welcome to this webinar. And today we are going to have a webinar on the topic of basic introduction to FEA. So in this, basically the main objective or main agenda of this will be to give you some brief idea of the FEA, like brief idea about the FEA. And this basically, this webinar is divided into 3 sessions. So first session is Introduction to FEA, in which I'm going to cover Introduction to Finite Element Analysis, type of analysis which are carried out in the FEA, stages to perform any FEA problem, we need, what input we need to perform that FEA problem, basic process summary, and then basic key concepts like equation of motion or stiffness matrix, how it get formed and how we can apply the stiffness matrix while calculating doing the FEA calculations. And then I'm also going to share best practices for modeling or simulating your FEA. In section 2 is opportunities for FEA engineers. So there I'm going to discuss about current trends and growth opportunities for FEA engineers. Then what softwares you should learn in the FEA, or what are the current softwares in the market. I'll give you that information. Then what are the work opportunities and industries in which we are widely using the FEA nowadays. And then I'll also share some critical skills required to get into this domain, so that when you come here or when you start exploring this field, you will come with some background or some basic prerequisites. And then the last will be the question answer session. As over there, if you have any doubt, you can just drop it into the chat box, and then at the end of the seminar I'll try to address those queries. So this is how our basic webinar is going to look today. And main objective of this webinar is to provide the basic overview process of the FEA. So when you complete this webinar, you will have some idea about the FEA process, what is FEA and how we carried out that. Then basic key concepts of the FEA. So if you start studying the FEA, this will definitely help you. Then provide the opportunities, information about the opportunities for FEA engineers, and then critical skills required to succeed in the as a FEA engineer. So all this, my main objective is to provide you all these insights, so that you will have some good learning about the FEA today. So let's begin with our section 1, that is Introduction to FEA. Okay, in first section, first of all, I want to basically tell you that why we need FEA, why we need FEA. So in engineering problem, or as a mechanical engineer, our duty, or when we are into core mechanical thing, our main objective is to design the component, to design the equipment so that it can sustain under given load conditions without occurring any kind of failure. Or if there is a failure, we should be aware that how much load it will take before it will actually fail. So that information we can get, when we want to have that information, we can get that information by using solution using either strength of material or theory of elasticity are normally accomplished for the regions and loadings with relatively simple geometry. We can get that information from the strength of material, but that is very relatively, we can use that for very simple applications because that is a formula based, and we have that is a basically simple geometry. We can say those formulas are applicable basically. So when in many applications involve cases with complex shapes and boundary conditions and material behavior, therefore we can say that in theoretically we can solve simple problems, but practically when we come in the practical component design world, we have the different scenarios, different complex component is there, complex geometries are there, the complex boundary conditions and loading conditions are there, and we want to predict the results for all these different scenarios. And at that time it is kind of difficult, or let's say not kind of difficult, or we can say impossible to do it with the when we use the analytical method. And therefore we can say that the gap exists between what is needed in the application and what can be solved by analytical closed form methods. So, and this gap actually leads to the development of several numerical methods. And finite element method or finite element analysis is one of the numerical method. So here is a brief introduction of why we need FEA, or what is the need of FEA basically. To summarize, we can say that to solve any engineering problem, there are three types of methods. So first is analytical method, second one is numerical method, and third one is experimental method. And each of this method has its own uh, positives and negatives. So if you go with the analytical method is a classical approach where we are using the closed form equation to solve any kind of problem, and where you know the error is zero because you are 100% accurate. You have the geometry, you have the formulas, and you are just solving it. So that is 100% accurate, but that is only valid for simple geometries, because for complex geometries you cannot do those complex calculations by hand. Second method is numerical method. So in this numerical methods, what we do is it's a mathematical representation of physical problem. Then it's a approximate assumptions mode. It is applicable even if physical prototype is not available. So when we say it is approximate assumptions mode, it means that we there are assumptions which we take into the considerations like material or boundary conditions, but those assumptions are very close to the real life problems. So in that case, though we have some assumptions, but still we can trust those results. Then it applicable if physical prototype is not available, we can have the CAD model and we can solve that. We don't need any physical prototype for that. Then solve real life complicated problems, and any kind of scenario actually we can simulate with the numerical method, but the results cannot blindly trusted. We must verify with the experimental method or with the hand calculations for the validation. So we can say it has very wide scope, but we also cannot blindly trust it, but we can get the solutions for a lot of problems by using numerical method. Then the third method is experimental method. In experimental method is an actual measurement method which we do in the lab. Then but it is very time consuming and it needs actual setup. It needs lot of prototypes. We need at least 3 to 5 prototypes we have to test before we actually say the results are looking good or results are trustworthy. We have to at least go for 3 to 5 prototypes, and it involves a lot of cost also as well as time. And basically the biggest disadvantage I can say for the experimental method, only experimental method, if we trust that we need lot of, if we want to go with lot of design iterations, then it takes a lot of time to complete that prototype, and which involves cost as well as time. So experimental method is there, but it is very time consuming. So if we compare all these three methods, so out of that numerical method is one of the best method which we are using nowadays to solve any engineering, mechanical engineering problem. Then what are the different numerical methods we are having nowadays? So we are having finite element method, boundary element method, finite volume method, and finite difference method. In finite element method, we find the approximate solutions to the boundary volume problems for partial differential equations. We actually here try to solve the partial differential equations in finite element analysis. Then in boundary element method, we analysis is done on the only on the outer surface of the body. Then in the finite volume method, it is mainly suitable for computational fluid dynamics. And finite difference method is, in that method we solve the differential equations, not the partial differential equations. So if we compare these four method, we can say that in boundary element method we are just solving it for the outer domain. So what is happening inside the body, we don't have the visibility by using the boundary element method. So over there we get the restriction for that method. Finite volume method is mainly used for the computational fluid dynamics. So if you have the structural problems, you cannot go with that method. Then finite difference method, here you actually solve the differential equations, and it is very difficult to solve the differential equation for complex geometry. For simple geometry you can do that, but for complex geometry it is really difficult. So the finite element method, which is basically depend on the solving the partial differential equation, is the best method out of all these four, which can give you most accurate results. So and that's why finite element method is so widely we are using in the industry. So for fluid dynamics problem we use the FVM, that is finite volume method, and for structural related problems, for thermal related problem, we go with the finite element method, as those are the methods which will give you the best results for any mechanical problem. Then now let's dig more into what is finite element analysis. So the finite element analysis is a numerical method for solving a problem of engineering and mathematical physics. For a given structure, the behavior of the structure can be described by governing differential equations. To approximately predict the behavior of the structure, it is necessary to find a solution of governing differential equations. So basically, finite element method is based on the discretization of the actual domain. So what we can summarize in a simple term is that in a problem domain is a collection of subdomains. Like if we have the big component or big domain, we are going to divide that or discretize that into number of subdomains called elements. We are going to solve the problem at each subdomain, then assemble element to find out the global solution, then assemble those equations, elemental level equations, to find the global solution. Solution is guaranteed to converge to the correct solution if proper theory, element formulation, and solution procedure are followed. So this is basically FEA that we have for continuous problem. We have a number of particles. We have a number of particles like infinite degrees of freedom, we can say. It is not possible to solve those infinite number of solutions. So what we do with the discretization, we are cutting the geometry into number of pieces. We are trying to solve those for that subdomain. We assemble those subdomain together to define the entire geometry. And then we solve the unknown basically, which we need from the simulation. Advantages of FEA analysis is predict product performance. Basically, how is for the given load, how your product is going to perform, how the stresses are looking, how the strain is, how the displacement is. So basically validate your design, reduce the raw material. If you find the stresses are too low, stresses are very low for the given material, we can definitely play with the thickness or other parameters so that we can cut down on the material and we can save the cost over there. Ensure optimal design, best possible design. By using the FEA, we can give the optimal design. Then we can use this method for verification purpose. It reduces manual testing and prototyping time because it is cut downing on number of iterations, design iterations, which you will actually need to build the prototype. So over there, you're saving a lot of time and cost, and you're giving the quick solution by using this method. This what if scenario. So you can study different type of scenarios by using the finite element analysis method, and you can foolproof your design by applying those different scenarios and seeing the results for those scenarios and validate your component is going to sustain for those particular scenarios also. And it shortened the design time. Absolutely, it shortened the design time, no doubt about it. So these are the advantages, and they are very promising advantages. And because of that, we can save a lot of time, a lot of cost, and a lot of efforts also. So no, definitely, and that's why nowadays we are using finite element analysis method so widely in the industry. Then type of analysis which we carried out are generally linear analysis, nonlinear analysis, dynamic analysis, buckling analysis, thermal analysis, fatigue analysis, crash analysis, and NVH analysis. So I would like to give a brief summary about each of this. So in linear static analysis, basically what we consider is that our load, whatever we are applying, is constant throughout the time. It is not varying with respect to time. Force versus displacement. If you plot force versus displacement, it has a linear curve, linear graph for force versus displacement, has a linear relation between them. What does it mean is like if for 1 Newton force, if you're getting 2 mm displacement, then for 2 Newton force you are going to get 4 mm displacement. That is a linearly related force versus displacement ratio. Then we can assume that it has all the linear properties, like it has material properties which are constant throughout the simulation. Its geometry is not changing. Its geometry is not changing, and it is not going under any nonlinearity in this simulation. So it is kind of very simple analysis, which we assume it is very easy to solve basically for the software. And over here, we can also apply the superposition method, and the results can be scalable actually. So the results can be scalable, and superposition method we can apply over here. So this is basically linear static analysis, but it is only valid for where you have the constant material properties, and where you have the not complex contacts are there, no non-linearity is present over basically over there. For that kind of scenario, linear analysis or linear static analysis, we can say, is very helpful. Then for nonlinear analysis is the analysis in which basically the we can say that load is constant, but load what we are applying is incremental in the software. Then we can say that force versus displacement ratio is not linear in this case. It is non-linear. We are going under, geometry is going under large deformation. So because it is going under large deformation, we have to consider the geometrical non-linearities. The changing shape of the geometry, we have to consider that when we are doing the FEA. Then here we also consider the nonlinear material properties. We can say that we have to specify the material behavior after once it crosses the yield point. What is the behavior? That behavior we have to define when we are saying mm, nonlinear material properties in the material. Like we have to specify the I will come to that, but it like plastic strain and yield strength we have to specify for nonlinear material proper nonlinear analysis. And then over here we also consider the boundary nonlinearity. Means if the components are changing their contacts, we are considering all those effects into this analysis. So in this analysis, you can find out a lot of convergence issues and a lot of skill required to perform nonlinear simulation. Then dynamic simulation is basically where load is going to vary with respect to time. And here the type of simulations we performed is modal simulation, frequency response simulation. And basically we also study in different type of vibrations in dynamic analysis. Then buckling analysis is one. Thermal analysis, where we want to find out the stresses occurred in the component when the temperature is changing. So what are the effect of the temperature changes on the stresses? That study we do using the thermal analysis. Then basically thermal analysis is useful for core engine components. It is very useful analysis. Then for large data centers enclosures, I must say thermal analysis is a very important analysis. Then fatigue analysis is generally for to find out the life cycle. For rotating components, fatigue analysis is very useful. Then crash analysis for car collision. Generally, we go for crash analysis, then NVH analysis. So, and there are many more, but these are the most popular and most used analysis which we do in the FEA. Then now, as we have little bit idea about why we do FEA or what is FEA, I'm going to go more details that stages of FEA. So there are basically, I say, 4 stages of FEA. Like we need a CAD model to build the FEA. We have to do the pre-processing. We are going to solve the solution and then the post-processing. These are the 4 main stages to perform any FEA simulation. So CAD data we have to take from the CAD department. Then pre-processing is the one. CAD data is like geometry. We are having our geometry to perform the FEA. Then in pre-processing, first step is that discretization. That is a meshing. We have to divide that domain into number of subdomains so that we can define our problem more properly. So that's why and we can solve our partial differential equations. And that's why discretization is very important step in the FEA pre-processing. Then apply the boundary conditions. Before applying the boundary conditions, you have to specify the properties, like so what are the sectional properties for this component, what are the material properties, you have to define them. Then you will go for the boundary conditions and loading, and then solution, what type of solution you want. That is, there you have to specify the load step, and you have to specify the step basically, where you will define what type of analysis I want to do, and what will be the output I'm interested in. All that data you will provide over there. Then after that we will go for the solution, where software will actually run the program at the back end and try to solve all those partial differential equations and give you the result for entire domain in the form of displacement, stresses, and strain. Then in the post processing, we are going to review the results, validate the results, and if we are finding the stresses are too high, or we are not the results are not satisfactorily, and we have to do some design changes, then again you will go back to the CAD cycle, and again you have to go for the CAD modification, again pre-processing. So this cycle keeps repeating unless and until you find the correct solution.